recording this before I forget. So if we, I'm trying to think of things that I did. Oh, I think I reopened the 4-4 guided learning through tonight. In case you either didn't do it, wanted to try it some more. Where am I trying to? Here we go. Not this. Letting people in. Children may have a slight meltdown. It's okay in the background. They're not dying, I promise. Yes, so the 4-4 guided learning opened back up through tonight. It did cut off last night. It wasn't that many questions, but it did have a trig one. So I wanted to bring back up a question from yesterday, wherever I wrote that. I don't know where I did that in notes. I gotta find it. It's somewhere. Was that one? One of these that we did. But now I don't know where I put it. Maybe in this one. Ugh. I had it earlier and now I don't know what I did with it. It was a trig one that we looked at. Well, crap. Did it get mixed in with pre-calc stuff? Well, I'll show you. Because I don't think we really answered all the questions. And we have some people adding, coming in after 1 o'clock. Okay, so I did add a 4-6 guided learning, and you should be able to do that by Friday. It's not that many questions. A lot of it is really easy polynomial stuff. But this homework 8 that is currently set to cut off, was that Saturday? Is going to be something that you should be able to finish by Saturday. And we can look at some stuff today from the 4.6 questions, Elizabeth, like you said. But it's really, the only thing it adds are rational functions, which bring up questions about domain and asymptotes and intercepts, which you've looked at before in pre-calculus, and we've sort of touched on maybe in the first chapter or two. But on the 4-4 guided learning, I really wish I knew where this was in here. I think I found it. Here we go. I'm going to share iPad with you now. We did this example yesterday. And I don't think it answered the full question, which is what I had a lot of emails about. So that was my mistake for not fully doing that one. But I think we might have run out of time. So this is similar to the one that's on the guided learning for everyone. And we did talk about it yesterday. And if you find yourself lacking in the trig things, I know I shared it with one student. I'm not sure how helpful it was, but there's lots of resources out there. If you don't understand how to use the unit circle, you should have already done that by now because we've had it in previous chapters, but you still need to know how to use it because of the trig functions that we evaluate with some of these questions. So what did not get discussed for this particular question? We went through, and I guess this was a couple parts. Yeah, we talked about finding its local min and max. We didn't really write down intervals where it was increasing and decreasing, which wasn't really the question, but it could be. And then when we did the second derivative, we found those critical numbers, and then we talked about their points of inflection, but I don't think it was really addressed about their concave up and down intervals, which is what a lot of people were emailing about. So just to follow up with that, and again, several of you have already asked about it, the big thing with this particular question is it was completely restricted only from 0 to 2 pi, because this is a sinusoidal. It'll keep going on forever with some kind of pattern. So we were only looking at the bracketed interval from 0 to 2 pi. So when you go to talk about where it's concave up and down, these pieces, you have to include the 0 and include the 2 pi. And we usually don't include values for concavity or increasing and decreasing, but on these trig ones, when you are looking at a set interval of numbers, you would say that this one was concave down let me maybe make some space here. It's concave down from 0 to 5 pi over 6 unioned with 11 pi over 6 to 2 pi, but the 0 and the 2 pi need a bracket or Sapling is not counting it right. Okay, and when you, the up wasn't the question, I think it was the down. The concave up is from 5 pi over 6 to 11 pi over 6, and you don't have to include those. But because of the 0 and the 2 pi ending, and that's what this particular trig function stopped at, then those were required to be bracketed for the software to count it right. So, but didn't go to infinity, but the acknowledgement that it only went from 0 to that point of inflection, and from that point of inflection to 2 pi was fine. But the Sapling, it appeared, needed the bracket or it counted it wrong. Okay, but I think that was a guided learning question. I don't remember which one, but it was on the 4-4 guided learning. Okay. The homework 8 that's up does combine 4.3, 4.4, and 4.6. And some of it is graphing, and a lot of the 4.6 questions, like I said, they just go into asymptotes and intercepts and the domain of questions, which we have talked about before. But now it's throwing it into the fact that you have to consider those when you make these charts, and we haven't really done a lot of that. So I don't think I wrote them on here. I had a few examples that I went through and looked at before right now, and I didn't know if you had burning questions or you want to wait till the end, and I'll see if maybe what we've talked about helps you, because there are some questions that show up that have to do with like quotient rule and power rule with different terms. So I thought, like I said, we could do some. And you are going to have a quiz over the weekend, but it'll be on a polynomial, and it won't be too hard, but it'll have all of those questions that we've looked at for this whole chapter. So maybe we should do like I'm trying to think of which one. Maybe a quotient one. I think there's some quotient ones, and I think there's also a couple of different terms added together. I'm trying to find the ones. I had some worked out. I think they were down here. Yeah, this is a good one. So here's a rational function of 2x minus 1 over x plus 1. So this is rational. It has some asymptotes. We've talked about them before. We did limits with these questions. If you look at the denominator, the domain is going to be everything except -1. Or if you wanted to do it in interval notation, -infinity to -1, -1 to infinity. It's just the domain for this rational function. The other thing that you could talk about, if you look at these leading terms, is the 2x over a 1x. This one ends up having horizontal asymptote. That's a highlighter. It has a horizontal asymptote at 2. It has a vertical asymptote at -1, but I mean, these are like pre-calculus things. So I think we looked at them some in the beginning of the first chapter or two when we were talking about functions, and we talked about limits because we were looking at end behavior when x went to infinity. So I know we've talked about them, but in the world of derivatives, some of that previous knowledge gets lost, but it's important whenever we go to try to describe the function. So if you wanted to try to figure out if this one had any local minimums or local maximums, or any sort of like, where does it increase, where does it decrease, points of inflection, its concavity. I mean, it may not have some of those things, but you can still figure out where it increases and decreases. Okay, so the increase, decrease in any kind of extrema that it may have come from the first derivative. So in order to do the first derivative of this function, we get to use quotient rule, which we haven't used in a while. So quotient rule, if you recall, does the derivative of the top, which is 2, times the bottom, which is x plus 1, minus the derivative of the bottom, which is 1, times the entire top function, 2x minus 1, all over the bottom function squared. And then you clean it up. And it's in a fraction form, so that's helpful. So if you clean up, and again, the purpose of the cleanup is so we can set it equal to 0 and find critical numbers. So if we distribute along the top, 2x plus 2, then a negative 2x plus 1 over x plus 1 squared. Our 2x's cancel, 2 plus 1 is 3 over x plus 1 squared. So talk to me about the critical numbers for that. Like if the question said, what are the critical numbers for this function, what would you say? And I'll take a chat, I'll take a talk, I got a 0. Move this over here. Anybody else besides Elliot would like to answer, give input? Critical numbers are, again, things that make the function equal 0, okay? Or what make them undefined. So in a rational function, anything that would make the numerator 0 is considered a critical number. It's a 0 of the function. And anything that makes the bottom 0 would make it undefined. So the numerator being 3, nothing is going to make that 0. So you're not going to get a critical number from the top. The bottom, you can get a value that makes the function undefined. So here at the top, this will never be 0. So we don't get any critical numbers from the top. And you can't see that. Okay. But from the bottom, x equals negative 1 makes the derivative undefined. But is it considered a critical number? Do you remember this little stipulation about making it a critical number? Anybody? I know I've emailed back and forth with a few people about it. Because it's important. Something happens at negative 1. But as far as listing out, is it a critical number? The answer here is going to be no. Brianna, yep, I thought maybe you would remember that. If the critical number is not in the original function's domain, it is not by definition critical. But I wanted to show you this example because even though it's not list all the critical numbers, it's not one of the answers, you still have to consider it when you make your chart. Because even though you're not going to have a minimum or a maximum there, it may change from increase to decrease, which makes it important for the first derivative, this test that we do for increase and decrease. But it's not important in the sense of the listing of the word critical. So we haven't had a lot of domain questions, but now we do. It's section 6. So it makes the function undefined, but it's not in the domain of the original f of x. So it's not technically, I'm gonna put it in some quotes here. It's not considered critical, but we'll still use it to determine increase and decrease. I don't think you can read that. Let me try that one more time with some more space. Still use for increase, decrease. So again, the listing of the critical numbers, you wouldn't say negative 1 because it doesn't make, it's not defined in the original function. But whenever we try to figure out where it increases and decreases, we're still going to use it in the number, which may be where some of you were coming up having some homework issues. So again, at negative 1, it's undefined. So I'm not even like, I'm just going to exit out, or it's not critical. I'm just going to exit out. I'll go below it. I'll go above it. If I plug negative 2 and 0 into the derivative, if I plug in negative 2 plus 1 and square it, it's positive, and it's 3 over a positive, so this one's positive. Or if you want, you can put a little plus sign there. If I plug in 0, it's still positive. So it appears that this function increases everywhere, but you can't say everywhere. There's a vertical asymptote at -1. So because this one's increasing, this interval is increasing, but at -1, there is a vertical asymptote from the original equation if you go back and look at it. So this is where some pre-calc stuff is going to come back in and be really helpful. So if you were to indicate intervals where it's increasing, you have to go -infinity to -1 and break it apart from -1 to infinity. You cannot say everywhere. You cannot put -infinity to infinity because there's that vertical split at -1. It's not decreasing anywhere, but you can't say it increases everywhere because it has an asymptote. Does that make sense? This is like what section 4.6 brings to the table. Is this added something else to consider? Okay. So if you go, and then as far as decreasing, I think I've seen, like on paper you could write none, but I think if there is no interval of decrease or increase, or the answer is nothing, I think you have to pull that little no solution symbol, or I think some questions ask you to put D and E for does not exist. But I think if there's D and E in the instructions, it'll tell you. And if you're looking for a set where it's concave up or down or increasing and decreasing, if there's not one, the expectation is to use that no solution because it's a set. Okay, so if you use your 5 attempts and realize that, just I'll reset them just to reach out. Okay, so there's no extrema. It increases everywhere around the asymptote. There's no minimum, there's no local min, there's no local max. So that's all the information we can get from first derivative. So now we'll do second derivative, because I would like to know where this is concave up and concave down. So if first derivative is 3 over x plus 1 squared, now we need to do concavity. Concave up, down, any points of inflection. I don't know, the second derivative will tell us that. So there's 2 ways you can do second derivative on this one. You could technically use quotient rule, I guess, if you wanted to, but I feel like it would be a lot of work. If you rewrote this as 3 with x plus 1 to the -2, you could do a really easy power chain combo. So f double prime would be -6 x plus 1 to the -3, derivative inside is 1. I mean, I just feel like this would probably be a little quicker than quotient rule, but you can do quotient rule. You'll just have to do a lot of simplifying. And if you need to ask about that later, you can. But we've done some of these in the last chapter. We did derivatives of these, so you're welcome to write this sort of power function with a power with a negative, and then just do power rule. Just remember to chain the inside if it's necessary. What would make the second derivative 0 or undefined? Again. Don't know. Nobody's typing. Looking for some participation. -1, -1. Yeah. So nothing makes the numerator 0 because it's just a number. If it had an x in it, we could set it equal to 0. But nothing would make the numerator 0. But -1 makes it undefined. And even though it's not in the domain of the original function, so it's not, again, considered critical, we still need to use it to test intervals to figure out where it's concave up and concave down. Okay, because it might be up and down everywhere. I don't know. I mean, I do know, but I'm saying if we did this guy again around -1, 0, -2, but instead looked at second derivative, again, now we're looking these values in second derivative. So if you plug in -2, here's where you have to watch order of operations and powers. So -2 plus 1 is negative. If you cube it, it's still negative, and a negative over a negative is a positive. If you plug in 0, 0 plus 1 is 1 cubed positive, you have negative over positive, so this one's negative. So this one does change concavity. The original function is concave up, then it changes to concave down, but at x equals -1, there is no point of inflection, but the concavity does change there. And I ran out of paper. Okay, so you can still do the test even though the number is not the critical and you're not going to get a point of inflection from it. It's still going to help you determine where the function is concave up and where the function is concave down. So it's up from -∞ to -1, and it's concave down from -1 to infinity, but there is no actual point where the inflection changes. I mean, there's no, like where the concavity changes, it's just the acknowledgement that it changes at that asymptote. And if you graph it, I think the graph does like, I think the graph is one of those rational splits where it is a concave up piece on the left and a concave down piece on the right, but it does increase everywhere except the asymptote. So again, these are the types of questions that show up in section 4.6 with the discussion of asymptotes and domain. And even though the number might not be in the domain and it's not considered or what the book is quoting calling critical, you have to use it when you build the charts and figure out the behavior of the derivative and the function. So I'll pause for questions, see if that helps. No, you're good? Again, I can't.
So I guess on the homework, if asked for the point of inflection, we would just put does not exist.
Yes.
Okay.
For that one, it would be, if it's a point, the point does not exist. If it's an interval, that's when you have to do the no solution. But yeah, it wouldn't have an actual point, like an XY point that you could slap into a coordinate to say this is where the concavity changes. And you wouldn't have to put that it's at the asymptote or anything like that. But you could still do it and get the information to find the concavity intervals. Okay. I'm trying to see, what are these other ones? There's one. There's one. I was trying to click through your all's homework before we got on today because nobody was really in office hours, which is fine. But I found, I had this one in my notes. Like I said, unless you just have one, feel free to ask. So this was a function, 2 over x plus 1 over x squared. And you could ask questions like, I'm trying to see what I did with this one before when I wrote it out. Okay, so it looks like the question here was just, are there any points of inflection? And I guess you could put S because maybe there's one, maybe there's more than one, maybe there's not any, I don't know. And you could graph it if you'd like to just see that there are, but then you'll have to use calculus to actually show what they are. So if the question just streamlines you to points of inflection, you can go straight to second derivative. You don't have to consider first derivative because all that information is going to tell you is the increase, decreasing local extrema, okay? And this is a sum of two functions. So you could second derivative them out and like rewrite them in powers, like 2 over x is 2x with a -1 and 1 over x squared is, I mean, you could do that and then the really easy power derivatives, but in order to do where the second derivative is 0, you'll have to make it one single fraction. So you can do that first or you can do that second. It's really up to you. Like what I mean do it first or second is you can make it into these terms with power functions, or if you make it into a single fraction first, you can use quotient rule, and maybe it's already in that single fraction and you can talk about where it's 0. So if you did that, the common denominator would be what, x squared? If you multiplied by x and x. So you're looking at the function 2x plus 1 over x squared. You can do quotient rule on that derivative. It's really up to you which one you'd like to do. But when you get down to finding where there might be points of inflection, you have to determine where the second derivative is 0. And if there's a few terms added together with fractions, you really need to make them a single fraction for you to understand where that's algebraically 0. So, I mean, I can do it with the power. First derivative is what? Negative 2x to the negative 2 minus 2x to the negative 3. Just don't forget, when you have power functions with negative powers, that when you bring it down and subtract 1, it gets more negative. I think I had some quiz mess ups on that. Second derivative is 4x to the negative 3 plus 6x to the negative 4, right? That's what you get with that one, which is really the same as 4 over x cubed plus 6 over x to the 4th. So I'm not saying that you can't find critical numbers from that and figure it out, but I feel like you might miss some stuff if you don't make it a single fraction. Because right now, nothing makes either of those numerators 0, and x equals 0 would make it undefined. Also not in the domain of the original function, but it would probably help with concavity and points of inflection. But that's not going to be the only one. And so if you can make that into a single fraction, then you can see what makes the numerator 0, which is why I try to stress for the first 8 weeks before the world got shut down semi-manner, is this ability to create single fractions if you had a bunch of terms added together. So for this one, if you made a common denominator, what would it be? A multiplication of x again? It would be, what, 4x plus 6 over x to the 4th? Right? Feel like I'm missing, maybe not. No, that's it. And if you set each of these equal to 0, again, you're going to get 0, makes it undefined, even though it's not in the domain of the original function. But the top is going to give you a critical number that you might not have seen leaving it split and separated like that. Because you're going to get, what is that, negative half. You subtract 6 and divide 4, or I'm sorry, negative 1.5 would be your number for this one. All right, 6 over 4, 3 over 2. Okay. So again, in graphing it, you can sort of see that that might be where it is. If we graph this function, I found Desmos back in my calculator. I think is that the same one? 2 over x plus 1 over x squared? Yeah. Do you see how that has, like, I wish I could follow. I don't know if you can see my mouse or not, but like the left piece is decreasing, and then it decreases to that low point, and then it bounces back up, and it has this asymptote. So, I mean, there's like a minimum here, which we didn't, that was first derivative stuff, but we were trying to look at where there might be a point of inflection. So like after that minimum, it's concave up, and it stays concave up, and the right half of the graph is concave up, even though it's decreasing. But the left piece, I don't know if you can tell, but it sort of bows to, for lack of a better phrase, it sort of bows towards the x-axis. So if there's actually a small, it's not really small, but there's a portion of it that's concave down, and somewhere, I don't know if I can trace, somewhere here, it flips to from concave down, and then this is concave up. And then doing that second derivative information tells us it's exactly at negative 1.5. Somewhere around here, if I can get it to be exactly. There we go. Oh, wait. Oh, wait. I think you get the idea. It's hard for me to keep this pencil on here. There we go. Okay. So the x value of negative 1.5 is where this one changes concavity. And I'm not sure you could have looked at this graph and been like, oh, there it is. Like you could on some of the trig ones. okay? And something to mention, I mean, we'll do the chart. 0, if you want to include 0, you can, because it might have changed concavity. So here's 0, here's -1.5, we'll go -1, 1, -2. And we can complete the chart. I know we looked at the graph. We're plugging this into second derivative now. So if you plug in -2, -8 plus top, so this part's negative. If you plug in -1, I think this portion's positive, and if you plug in 1, it's still positive. So you can sort of see where the original function is going to be concave down, concave up, concave down, just kidding, concave up. So there's not really any point of inflection at 0, and it doesn't change concavity there. Plus it was an asymptote to begin with, a vertical. But at this -1.5, -1.5 is in the domain. You have concavity change from down to up. The -1.5 is the point of inflection, like that's where it happens. So the point of inflection, if you had to give the actual XY point, -3/2. Again, do you remember how you would get the Y value for this one? Zoom back out. I got a chat. Open it up. Plug it into the X where? You do plug it in. Yes, Olivia, the original function. So you'll take this fractional or decimal value and you'll evaluate the original function at that number. So we'll get to some ugly on the outside, but pretty on the inside functions where I think even Sapling will take it. If you acknowledge that you are just doing the function evaluated at -3/2, that's sufficient for an answer. If you wanted to plug it in for the function, again, Desmos has this really awesome capability. If you define the function as f of x, your calculators will do the same thing, it's just a little different. Then you can evaluate the function at -1.5. If you type it in correctly, you can. Which it's -0.8 repeated. And I don't know that some of you are that savvy with your repeating decimals, but if you fraction it, it's -8/9 exactly. Like you have to be able to give the exact fractional answer for these if at all possible. And plus, I think that was the number that it pulled when I tried to sort of go in here. Somewhere around here, -1.5. There it goes. It says -0.889, but that's a decimal approximation. The -8/9 is exact. So that's what you would be expected to give for the actual point. And some of your homework, I noticed it wanted the actual point of inflection in a coordinate point. And some of the questions, like towards the end of that homework chunk, only wanted the X value where it was a point of inflection. So again, just pay attention to what the question asks you for, because some of them, especially when we get into the ones with the radicals, they are not nice. Or the natural logs, they can be a little hairy to try to come up with function values using log properties. Okay, but this one was just a point of inflection. It only had one. Second derivative gave it to us. But anytime you have these rational functions that you can turn into powers, if you can make a single fraction, it's really easy to figure out where the derivative is 0 from the numerator or undefined in the denominator. Okay. Do you have questions? Do you have any that you want me to look at? I mean, I have some more written down from your homework. There's one with an E. Oh man, what the heck did I click on for that? Come back, 1110. Oh, seriously. I'm done with this iPad this week. I don't even know where we were. This guy, maybe? Okay. Jeez. Okay. Nobody has written anything. Nobody has talked or anything. you want me to just keep doing another one that I had written down? Sure. Like I said, you guys got to ask. So I got a natural log, or I got a quote. Actually, they're both quotient rules. Or an E. Oh, some chats. Let's see what you say. All I have is yeah. Okay. So no specifics. So I have one with a natural log, and then I have one with an E. Maybe I'll do the E one. X over E to the 7x. That one was a fun one. This one actually, it's from your homework. Again, I was clicking through it right before class, and I literally forgot what I was going to write. Gosh, brain. Okay, X over E to the 7x. So this question that's in that homework 8 only asks you for the X values of any inflection points. So if there's not any, you'll put does not exist. If there are more than one, it basically just wants you to find the X values. You don't have to plug them back in to get the actual point of inflection. It just wants any X values where this may change concavity. If you want to graph it and see how many there might be, just guesstimating on the way that the concavity changes, you can. But if we want inflection point information, we need second derivative, and this is a quotient, okay? So I know, again, it's been a while for some of you since we've done quotient rule, and maybe some of you weren't too keen on it before, but it's top derivative times the bottom minus bottom derivative times the top over the bottom squared, okay? So what that looks like for this function. First derivative of the top is 1 times the bottom minus the derivative of the bottom. It's going to be, so e to the x derivative is e to the x, but when it had e to a quantity, you had to do chain rule. So it's e to the 7x times 7, and then don't forget to multiply the x. That is what I'm afraid a lot of people will forget. Like if this is f and this is g, here's f prime times g minus g prime times f. I mean, if you need to make yourself that little fill in the blank so you don't forget it, then I would do it so you don't mess that up. And that's all over e to the 7x squared. So power to a power, you multiply, and you can make it 14x if you wanted to on the bottom. I'm going to leave it because I'm noticing that all of these have an e to the 7x. So I can do some algebraic canceling before we go too far. So if I factor that out, this e to the 7x, I'm left with 1 minus 7x all over e to the 7x squared. And the reason I didn't do the power to the power is because here I can cancel one of those on the top with one of those on the bottom. Okay, and you're allowed to do that if it's a product and it's the same quantity and you can cancel, but I don't want you to, make the mistake, because some of you are not the greatest with algebra and we need to get you a little bit stronger with it, which is hopefully what this course is trying to do for you, to move forward a little more successfully. So for this one, I mean, this is first derivative. If I'd wanted minimum, maximum, extreme, increase, decrease, I'd need to go through, figure out a critical number, but that's not what this question says. If it did, you could set the top equal to 0 if you wanted to, but it doesn't, so we're not. We're just going to keep going on to second derivative, because our first derivative is 1 minus 7x over e to the 7x. That's our first derivative. Okay, so then when we do second derivative, we're doing it to that quotient again. So we'll use quotient rule again. And up here we use quotient rule. Okay, so the derivative of the top, it's linear. It's a 1, which the derivative is 0, and it's a negative 7x, which the derivative is just negative 7. So you've got negative 7 times e to the 7x minus e to the 7x times 7 times the quantity of 1 minus 7x. Again, if you need to write out that little f prime times g minus g prime times f, do it so you don't lose track of what it is that you're writing. And then that's all over e to the 7x squared. Okay. So now I think we have the same thing that we had before, in that everything, like all of these places have an e to the 7x. And if I factor it out, I should be able to maybe cancel some stuff. You can cancel it here if you want to, but I would rather factor it out so you could see it. So if I factor out an e to the 7x, I've got a negative 7 minus a 7 times 1. It's a whole lot of 7s happening right now. It's supposed to be lucky, right? Just kidding. We can divide away one of the e to the 7x quantities from all of those places. So this one's gone, this one's gone. And our top, if you cleaned it up, would be what? Negative 7 minus 7 plus 49x all over e to the 7x, right? And that would clean up to be negative 14 plus 49x. I guess up here you could have factored out a 7 if you wanted to, or a negative 7. Some of you may have done that, because now this 14 plus 49x over e to the 7x, we need to figure out where it is 0 or undefined, because we're trying to figure out points of inflection that could happen. So I think we talked about this yesterday. I'm pretty sure we talked about this yesterday. E to the x, or even e to the 7x, will never equal 0. E is an irrational number. If you raise it to a power, whether the power is positive or negative, it's still going to be positive. So it'll never be 0. So that you're not going to get anything from the bottom. The top, though, if you set the top equal to 0, negative 14 plus 49x, so that 49x is 14. Divide by 49, you should get the number 2/7. And so that's really the only number that makes that second derivative 0 or undefined. And if you go through the motions to verify that it is a point of inflection, go below, go above. If you plug 0 into, again, these are going into second derivative. If you plug in 0, up top it's negative, and on the bottom it's 1, so this is negative. If you plug in 1, this is positive. So yeah, this is a point of inflection. You're changing from concave down to concave up, and the x value of 2/7 gives you a point of inflection. Doesn't want the whole point, just wants the x value where it happens. That's the only one, is 2/7. And if you were to graph it, which I don't think I did, so I don't even know what this mess looks like. And I forgot the function. Oh my gosh. X over e to the 7x. X over e to the 7x. What? Look at that funky thing. It's almost like a logarithm graph, but it's got a hump in it. So over here, so it's concave down to begin with, and then it does have a maximum. It has a local max there somewhere. I'm guessing that's what that point is, which is some form of a 7th. The point of inflection happens at 2/7. So 2/7, I don't even know what that is, because 7ths are a weird decimal. 0.2857. So somewhere, oh, come on, Desmos. Are you really not going to let me do this? 2857, 28. Somewhere in here, it flips from concave down to concave up. But I'm sorry, there is absolutely no way that you can just look at that and tell that. You'll have to do the calculus to pull it exactly. So somewhere here around 2/7, it's like 0.28. Somewhere in here, it actually flips from concave down to concave up. And this is your show me calculus to show your answer. Okay. So quotient rules back, logarithms are back. I haven't seen a lot of inverse trig in this chapter yet. which I guess could be a good thing for some of you. And it's 1:47. Any last minute questions? Because we have tomorrow. Tomorrow we can do more, or tomorrow we can save it for full questions if you guys want to ask. Again, some of these are they'll do domain. The intercepts, like, where's one that we did? Did we do this one? Or did I do this one? Where's one that I did with you? Here's one that I did with you. So like this rational function that we did to begin with, again, it might ask you the domain. I don't remember if it asks you for asymptotes, but it's good that you understand that they're there. If you had to do x-intercepts of the graph or y-intercepts of the graph, y-intercepts are what you get when x is 0. So if you plug 0 in for all the x's, you'd get a y-intercept of -1. X-intercepts for rational functions are where the numerator is 0. So if you set the top of the original function equal to 0, I think you get an x-intercept at 1/2. So those are the kinds of questions that show up in the 4.6 where there's like 8 answer boxes. It'll ask you for the domain, it'll ask you for an x-intercept or a y-intercept, but that's what these are looking at. And some of them are polynomial related, some of them are rational. I think I saw one with a natural log. We can look at it tomorrow if you want to. But I'm not trying to spend all of your class time doing your homework for you and showing you how to do every problem of your homework. I would like you to actually apply what we talk about to doing your own homework. And as of 1:49 on this beautiful Wednesday, we have, if Sapling will load, there are, oh my gosh, they must be on the internet. There are 13 of you that have started your homework for this chunk of homework. So please start your homework. Math Lab is open 4 to 7 p.m. tonight through a Zoom session. The information is in As You Learn. The online 8 to 11 p.m. is open. If you want them to help you with trig refreshing, if you need them to help you with this rational function algebra, I mean, you have to acknowledge what you are weak at and then ask for help on it. And they can help you, I can help you, but you have to start your homework, guys. I don't know how else to, I've said this all semester, and I'm going to keep saying it till May. You need to do your homework. I don't know how else to say that. I haven't really updated. I don't think I've graded your quiz yet. I've been grading some pre-calculus quizzes. So I'll be working on that this week for the quiz that you took online. I did input your Google form quiz completion, the Google form that I had you fill out by Sunday. That was a quiz grade. So it's up there. It's in As You Learn for a quiz grade. So maybe that helps some of you because that's like a straight 100 on a quiz right there if you did it. But you're good? Best you can be in the situation that you're in. You're not going stir crazy yet? No? Okay. Crazy is a relative term, right? I'm going to go do some, oh gosh. Is your joke appropriate? Okay. Is it clean? Okay. Jeremy, what's your joke? Should I stop recording? I can always edit it out. CVS. That is true. Where else gives long receipts anymore? Is it Walgreens? CVS might do it too. I don't know. That's a good one. I got an April Fool's joke I'm going to show my kids that had some superintendent of North Carolina schools saying they were going to make kids repeat the grade that they're in right now. It's like a whole press conference and everything. And if you click on it, it's like on Facebook. And if you click and read on it, it's like, haha, hashtag April Fools. And they are going to flip out if I show them that, especially my 3rd grader. But anyway, that's a good one, Jeremy. Thank you for sharing. I'll upload the video if you need to watch it later. I could try to upload some of these notes because I don't think some of these questions are up. I mean, you can watch the video if you want to see them, but I think some of you like watching the actual flat notes. And if you, like I said, you get into your homework and you don't understand where you've gone wrong, just please send me an email with a picture. I'm happy to look at it and hop on and try to help you if I can, as long as it's not during supper or baths or at 11 o'clock. I don't know. I was up at 11 last night grading quizzes. So you let me know how I can help you, okay? Is he gonna type more? Okay. You're good. All right. I'll see you guys tomorrow.
Hey Puckett.
Oh, Tiger King. I have not watched that.